आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़, की आवाज़।
Vigyan Ki Awaaz podcast series aims to popularize new ideas of science and technology, which highlight STEM, science, technology, engineering, mathematics, and medicine. This brings to the surface the efforts and researches of Indian scientists, which is desired to bring a change in community learning and teaching, access to knowledge of resources, and social paradigms. Our goal is to spread the name of indigenous Indian research stories and their masters among the masses of society in a very easy manner. Bose Institute was set up in 1917 by Sir Jagadish Chandra Bose, the founder of modern science in the Indian subcontinent. It is Asia's first modern research center devoted to interdisciplinary research and bears a century-old tradition. The institute was founded as not merely a laboratory but a temple, with its principal aims being the advancement of science and diffusion of knowledge. Swami Vivekananda, Sister Nivedita, whose influence is reflected in the institute's emblem of Vajra, was significant in the setting up of the institute, and Rabindranath Tagore were among those who had consistently inspired and supported Jagadish Chandra Bose in his endeavors. Ever since the establishment of the Department of Science and Technology, Government of India in May 1971, Bose Institute has been an autonomous grant-in-aid institution of DST. Over the last century, the institute has endlessly strived to preserve the legacy of its illustrious founder. In this podcast, we are happy to present Professor Anup Kumar Mishra, Professor and Chairman in the Department of Chemical Sciences in Bose Institute. But before going into more details about his research work, let us hear from his own voice about his academic journey.
Myself, Anup Kumar Mishra. I spent nearly 14 years in Bose Institute, Kolkata. Before that, I spent about 7 years in Central Drug Research Institute, CSIR Institute in Lucknow. And before that, I was working as a postdoctoral fellow in the Barnum Institute, San Diego, California for 2 years. And before that, I was also in UK for a year. And I did my PhD in the area of carbohydrate chemistry in the Indian Association for the Cultivation of Science, Jadavpur, Kolkata. So now I will continue some more years in the Bose Institute and try to contribute some. I will talk about my group's research activities in the area of medicinal chemistry, utilizing the commonly available sugars or carbohydrates for the development of some therapeutics which are which can be used and which have been used also for the treatment of different diseases, as well as to have been used also as some vaccine kind of molecules.
Vaccine has been one of the most talked about topics in the post-pandemic era. Let's get into details about Professor Mishra's specific area of research.
If we consider the therapeutics as a whole, it's in general two kinds of therapeutics. One has a short memory, another has a long memory. The short memories are generally we term it as the drugs. These drugs means or pharmaceuticals. Those are being used to control or to manage any irregularities happening in our body, or to protect us from the infectious diseases or from lifestyle diseases like diabetes, cancer also, lipidemia and all these things. But the long term therapeutics generally includes the vaccines, we term it. These vaccine molecules generally concept is that once you take, and it will be you will be protected from that disease for years after years. And as a result, this vaccine has much more interesting properties also to develop this kind of molecule. However, very few vaccines are developed by this by today against various diseases, mostly in the area of infectious disease, be it antibacterial, be it antiviral, antiprotozoal, something like this. So in that sense, the major emphasis can be given to the development of novel vaccine candidates together with the development of the small molecule therapeutics or drugs.
Professor Anup Kumar Mishra reveals some interesting information regarding vaccine. Let us hear from him.
Okay, so by training I am an synthetic organic chemist, and I worked in the area of synthetic organic chemistry using the carbohydrates or sugars as the substrates. And we have used for long years, we have been working in the area because of the fact that this polysaccharides, which is one of the major biopolymers in our natural system, and those molecules showed the property of antigenicity. What is that? That if we take one example, for example, if our cell wall, if we consider ourselves as the host, our cell walls is composed of several polysaccharides, as well as the microbial organisms like bacteria, virus. Those are also having cells which are also coated with the polysaccharides. And this when the bacterial species is coming in close contact to a host, what happens that the signal transmits from the bacteria to host or from the host to bacteria is being done through the interaction of the polysaccharide molecules present in the outer layer of their cell. Since this is the first stage of the adhesion of a bacteria to a host, that means they are coming close to the host, and then they will sit on the host, then they start infecting the host. This is the general mechanistic approach. Since these polysaccharide molecules are mediating the interaction between the host and the bacterial species or viral also, these are the molecules which can be useful for developing something which can be used as the antigens to develop antibody against within the host body, so that in future when the real organism having similar polysaccharide architectures in their outer layer will approach to the host, that will be defended by the antibody present within the host by the use of synthetic molecules. That is the main objective of this kind of polysaccharide based vaccine development. And till date, there are many vaccine candidates are in the clinics, and most of them are actually protein vaccine, and few are also nucleic acid vaccines, and of course few are from the polysaccharide based vaccine. For example, polysaccharide like hemophilia influenza type B, in short HIV vaccine. Nowadays every child is getting this vaccine because that is a polysaccharide vaccine. That is, in earlier days it was seen that this outer layer polysaccharide, if one can isolate it by the culture of the bacterial strains, and if that can be administered to the body, intravenous system, that can develop some antibody in the body. But that is not good enough to protect the real infection of the microorganism, because in general the polysaccharides are not antigenic mostly. So to develop because the antigenicity works through the involvement of the T cell or B cell in our body. So to make it independent of T cell or B cell, which is not available in the children, because these cells are not generated below 5 years or something. So the most important thing is we have to vaccinate our child so that he or she will be protected from the upcoming infections. So how to do it? So, and again we know that the polysaccharide itself cannot do the role, but it can be used as the antigens or the vaccine, kind of antigen or vaccine, if we can conjugate it with a protein. Which protein? That protein which is beneficial in our system. And the FDA has identified only 4 proteins like this, which one can use for the conjugation with a particular polysaccharide chain for the development of a vaccine candidate, because all are chemical approach. This is not any natural processes. So to that proteins are actually like tetanus toxoid, which we take always for this tetanus to protect us from the tetanus, from any cut or something injury. And another is diphtheria toxin. And another is E. coli recombinant protein, which is being used also as the protein component for conjugation purpose. Protein, why we use protein then? The protein actually that will lead the molecule towards in our system, immunity system, to develop, to make, this is a kind of transporter, and to take it for this molecule to the immune system, so that the immune system will recognize that protein, and through recognition of that protein, that whole entire conjugate will be recognized. And for this purpose we use 2-3 proteins also this is. And you see, one can say that why you need to do it chemical synthesis in laboratory, because to get the polysaccharide molecules you have to only source is the bacterial strains, which are virulent in nature, because we are trying to make something to protect us from them. So if we need to culture them, it has some drawbacks in it. One thing is you have to handle the live strains of virulent bacterial strains, that is the worker who will work is very prone to get infected. Another thing is this polysaccharides chains, it's a long chain molecule. If one can isolate it from the natural sources, there would be a possibility of having impurities like biological impurities, maybe some lipids, some proteins, some peptides, there are many others. So it is very difficult to isolate or to purify the bacterial isolated polysaccharide molecules. And the third and important point is that the lack of homogeneity. It means that every time you may not be getting the similar chain length of the polysaccharides, and that may affect the development of antigenicity of the entire molecule after making a conjugate molecule. So the idea is to make it in a safer approach, because another thing we should remember that this medicinal chemistry or drug discovery in general, what I feel that it should follow 3 E's. One is it has to be the effective or efficacy should be very high. Second is it must be very economical. And third is ideally it should be everlasting.
Professor Mishra shares with us some of his important studies about the relation of a synthetic organic chemistry with a medicinal chemistry for the development of vaccine.
So in a synthetic organic chemistry, if a organic chemist can plan to get the structural information of that polysaccharide from a virulent strain of bacterial species and can, because it then plan synthesizing it in the laboratory, that can avoid the problem of heterogeneity of the isolated polysaccharide molecule. Second point, that can avoid the handling of the live strain of bacteria. Third point, that can avoid the lack of having enough quantity from the natural sources. Because if a concise chemical synthetic strategy can be developed, one can prepare in a terms of kilogram, grams, milligram, whatever like. So that is the relation of a synthetic organic chemist with the medicinal chemistry for the development of the vaccine candidate molecules.
The achievement of Professor Anup Kumar Mishra has immense contribution to a largely populated country like India.
We have been working some time back on the meningitis. Is a serious problem, not only in India, in everywhere, mostly in India and mostly in the African countries. And there are many small molecule therapeutics which is not enough. So you need to have a vaccine kind of. So that the structure, this what I am saying, this polysaccharide molecules, this is not same for all bacterial species or all virus. Every bacteria, like say if we consider E. coli, E. coli has about more than 200 serotypes, we call it. Serotypes means this depend, they are classified based on the structural polysaccharide molecule in their cell wall, like that. So all are not actually virulent or pathogenic. There are many are very, very beneficial to us who are existing in our gut actually, and they are helping us to get digestion of foods and all these things. But when the immunity getting compromised, then they will, some of them may become virulent and effect. So in my experience is that we have developed some molecules which were these polysaccharide fragments synthesized in the laboratory, which was connected to a protein that is actually, which, as I said, that tetanus toxoid, and that was in collaboration with actually Wellcome Trust Laboratory. And those were, although it was done in India laboratory, but targeted was for the application in the African countries for their other area of. And secondly, we used some salmonella infection, salmonella kind of vaccine to control the because when we get stomach problems or the gastroenteritis, we have many bacteria. We may say cholera, it may be dysentery, it may be salmonella, it may be E. coli, there are many. So we decided, it was an NIH project. We had I have a collaborator in US. So we developed some molecules. In that case, we intentionally used a protein which is not FDA approved. We used the tobacco mosaic virus's viral coat. That protein, we killed that virus and I isolated that protein coat for conjugating it to make a glycoprotein conjugate vaccine candidate, and to see that how it is raising antibody against this kind of molecule in rabbit.
Professor Mishra speaks on the way forward.
So we are quite successful. We filed a patent, but it is not yet published. So this is one, and we are working still. We are working in this area. And lastly, I would say that although we are working in the medicinal chemistry, and our theme should be for the direct benefit of the society or human population. At the same time, we train people for working in this kind of area in the near future or distant future. So students are doing PhD work also under this kind of program, under our supervision. And accordingly, they are going out. There are few students there. By this time, they are settled outside, and some in companies, some are in academia also. So that's in brief, I can describe my work in Bose Institute.
We are thankful to Professor Anup Kumar Mishra for providing with us his valuable time and information on his field of research.